So high level, what are the different ways to build a nuclear fusion power plant? So can you explain what a tokamak is, what a stellarator is, and what's the linear approach that Helion is using?
So there are a number of ways to do fusion. And fundamentally, in all fusion approaches, you're trying to do the same fundamental physical process, which is take these lightweight isotopes, heat them up so that they can move at high velocity, over 100 million degrees, bring enough of them together. We call it density, enough of them together in a certain volume so that you have reactions happening at a high rate, and keep them together long enough that they are able to collide into each other and do fusion and release energy. That's the fundamental core. Now, how you do that, how you bring those particles together, how you hold them together long enough, there's a wide range of technologies that, as humans, we've been exploring since the 1950s. And I think about several main categories. If you look at the fusion funding out there, government funding in the world, private funding actually has quite a different profile, which is an interesting thing to talk about. But in public funding and federal funding in the United States, there's two mainline programs called inertial fusion and magnetic fusion. And in inertial fusion, what you're trying to do is bring together and push together by a variety of means, physical means, those particles. You push them together. The most common is called laser inertial fusion. Our colleagues at the National Ignition Facility did this really well and made world records in the last few years for being able to demonstrate you can do this and do it at scale, where you take very high power lasers and pulse them together to combine them to do fusion for a pulse for a very short period of time, nanoseconds, billionths of a second. The other extreme, and you mentioned tokamaks and stellarators. Stellarators are actually my favorite. So we'll talk about those. Graduate student in fusion, the stellarator is the first thing you learn about because there's a mathematical solution for a stellarator that solves perfectly. And you can write it out and you can solve it, and analytically it's very simple. Building one is very hard. And so it's taken humanity a number of decades to be able to build stellarators, and we can do it now with the Windelstein 7X that came online in the last few years, being the premier stellarator in the world.
I should say all the different ways to do fusion all just looks so badass in terms of engineering, creating this containment, extremely high temperature, high density. Everything's moving super fast. Everything is happening super fast. It's just fascinating that humans are able to do it. Like, there's certain things, accelerators of that a little bit, but this is even cooler because you're generating energy that can power humanity with this machine. Anyway, can you just speak a little bit more to the inertia and the magnetic fusion systems?
In a magnetic system, your goal is not to push together those particles as fast as possible. Your goal is to hold on to them for as long as possible. And to do that, we use magnetic fields. So let's take a step back. What is a magnetic field? So in an electromagnet, there's a variety of ways to make a magnetic field. One of the most famous, I think everyone is familiar with, is Earth itself. Earth has what we call the magnetosphere, which is the magnetic protection that's generated actually by the core of the Earth. But we have a magnetic field around the Earth. And that magnetic field protects us from particles coming from the galaxy, galactic cosmic rays and solar particles that would come to Earth. That magnetic field, when you run a compass, you see the magnetic field from the Earth. So we know it's happening. It's all over. But how we generate it with electric currents is a little bit different. And what we do is that we have a loop of wire. And the simplest way to think about it is literally a round loop. And in that loop, you have electrons. You have an electrical current that's running. And when electrical current, this is some of Maxwell's equations that we discovered in the 1800s, that when you have an electrical current in a wire, it generates a magnetic field inside that wire. And so when you look at fusion systems, you always have these big magnetic coils with large amounts of current. We don't run a little bit of current. In our systems, we have hundreds of mega amps of current. If you think about at your house, you have your breaker box with 200 amps or maybe a 400 amp breaker box, and we run 100 million amps of electrical current. So massive amounts of electrical current to be able to do this. So that magnetic field that's generated inside that magnetic coil has some really special properties. And we take advantage of those properties to do fusion. And some of those properties are not intuitive. So here's one of my favorites. When you have an electromagnetic field, you have this coil with electricity going around it, and you have a magnetic field inside of it. And then you have a test particle, a charged particle, an electron or an ion, which is, if you imagine, to generate this, I have a coil with electrons moving around it. But if I put one in the middle of it, in this magnetic field, some really interesting things happen. That electron or that ion, that charged particle, is what's called magnetized. And what magnetized means is that it's trapped on that field line. In fact, even really more interesting is that it oscillates around that field line. And so the way I think about this is if you think about the Earth's magnetosphere again, and you think about the charged particles, the aurora, the northern lights, is a charged particle trapped in the Earth's magnetic field going around the Earth's magnetic field. And in the same way in fusion, we do the same thing here on Earth, but in a smaller direction where we trap these particles on magnetic fields, and they can go around and stay trapped to that magnetic field line.
How much of the physics at this scale is understood here? Like how these systems behave when you trap the magnetic field in this way? Like, is this fundamentally now an engineering problem, or is there a new physics to be discovered about how the system is behaving?
In fusion, the physics we're using is actually quite old. That the fundamental electromagnetic physics is 1800s physics. The fundamental atomic physics is early 1900s. And so the fundamental physics of how these work is very well understood. Putting them all together into a power plant, that's hard. And so you can do the math. You can do the math. Every introductory grad student does the math on a stellarator and say, this is all I need to do. I just need to make a magnetic coil in this very complicated shape. And then fusion will happen. However, doing that in practice is actually quite challenging.
So maybe you could speak a little bit more. So the stellarator and the tokamak, what's the difference between those two? They're both magnetic fusion systems. And then what does Helion do?
The tokamak and the stellarator are both magnetic systems. Their goal is to generate this magnetic field and hold on to the fusion fuel long enough. Like I mentioned, these charged particles are trapped on the magnetic field. In fact, they're oscillating. We call that a gyro orbit, as the radius that they oscillate around this magnetic field. And we've been talking about atomic physics, where everything is at this nano scale. But gyro orbits are not. Gyro orbits for these fusion particles are measured in inches. And so they're on a scale that we can see and measure and understand really intuitively. And in a magnetic system, your goal is to simply trap as many of these particles as you can for long enough and heat them so they're hot enough so that they bang into each other. They collide enough that you're doing fusion. And you're doing enough fusion to overcome as fast as you're losing those particles. And so that's what happens when you put particles in a magnetic field and you try to hold on to it. The challenge is that's really hard to hold on to them long enough. These particles are moving around. They're moving at very high velocity, millions of miles per hour. They're colliding with each other, and they're getting knocked off and getting knocked away. So we've talked about inertial fusion, where you try to confine a fusion plasma by crushing it as fast as possible. And magnetic fusion, where you just simply have a magnetic field, and your goal is to hold on to it for as long as possible. But there's another way to do fusion. And in some ways, it's one of the earliest approaches for fusion that was successful. As scientists and engineers, maybe we're not too creative with the terminology. We call the technique that Helion uses magneto-inertial fusion, because it does a little bit of both. So to understand that, we can actually go back in history a little bit and think about the evolution of some of these approaches to fusion. And so from our perspective, we look at the technology that we use as built on physics experiments that were very successful in the 1950s. And in those systems, the earliest pioneers of fusion said, we understand the physics. We have to take these gases, heat them to 100 million degrees, and then confine them, push them together so that fusion happens. And so, what is the best way to do that? So, some of the earliest programs, we called them the theta pinch. And what those programs were a linear topology because we knew how to build these magnets. It's called a solenoid, where you take a series of electric coils, you run electrical current through them that generates a magnetic field. Great. So, you have a magnetic field. Now you add your fusion particles, okay? So you've added fusion particles to this solenoid. Here's the challenge. Those particles, as they're sitting in that magnetic field in this nice magnet, escape. They leave out the ends because there's nothing holding them in. Great. So that makes sense. And so that doesn't work, okay? So then the next approach is say, well, one branch of fusion said, okay, well, to solve that, why don't we take this solenoid and bend it around? Let's just make it a big donut. So as they're escaping, they go around and around in a circle. Great. That's a great approach. And so one branch of fusion went down that direction. And that evolved into the stellarator and the tokamak, different ways of taking those solenoids and wrapping them around so that the plasmas go round and round in that magnetic field and those charged particles are held long enough that fusion happens. But there's a different way to do it. And so the theta pinch was what was born in the 1950s of take this magnetic field and, they're trying to escape. Great. Let's not let them escape. Let's close the bottle.
Mm-hmm.
Let's close the ends. And so we make the magnetic field much stronger at the ends. This one was called the Miro. And so the idea was that the particles would bounce in between. And that worked. And they got hotter and hotter and hotter. But guess what? As you kind of would imagine, as this mirror topology, this linear topology, the pressure increased inside. The particle pressure, the particles tried to push back on the magnetic field. They were trying to escape now. They're getting hotter and hotter. And just as you imagine, hot gas in a balloon tries to get out the ends, and you could not hold it tight enough at the ends to keep those particles in. And in fact, the problem is the hottest ones were the ones that would escape.
Mm-hmm.
And so you do a good job of heating it and they'd all leave out the ends. Okay. So then the next iteration has said, okay, well, why don't we just not try to hold on to it very long? Why don't we squeeze it? And so rather than just holding it constantly, let's now crush it. So we built this solenoid, we pinched the ends, and then we crushed it. And what I mean by crushing it is not actually like crushing any magnets or changing the topology or moving any parts, but just rapidly increasing the magnetic field. And so going from a magnetic field that's just holding it to now taking all those particles, if you imagine they were in a streaming around together, and then rapidly increasing the magnetic field so that those particles get closer and closer together. So you increase the density. And now fusion starts to really happen. But they ended up hitting a technological limit. So this is the part that I look back and I look at the pioneers that in 1958, there was some pioneering work done. And this was in California, what later became Livermore Labs. There was also some work done at other national labs too. These were all federally funded programs to explore this theta pinch topology of can you just squeeze the plasma down fast enough, hard enough? This was 1958. The transistor was sitting in the laboratory and they were commuting. They were turning on millions of amps of electrical current. And they were doing it. We haven't talked about the timescales, but they were doing it in millionths of a second, microseconds, megahertz speeds. And this was in 1958. No transistor, no CPUs, and no electrical switches, none of the things that I take for granted every day. And so they were able to show at that time the highest performing fusion systems. They got to temperatures. They didn't get to 100 million degrees, not quite then, but they got to 50 million degrees. They were outperforming everything else in fusion, but they reached a technical limit where they just could not build it anymore. And so those pioneers went in a different direction. And they started down the laser inertial path of saying like, okay, well, we can't do these electromagnetic pinches, but we now have this new thing has invented the laser, which turns on in a nanosecond. It's fast. It's interesting. Let's go down that path. And it's not, you have to fast forward a couple of decades to researchers found with some of these theta pinches, when they're operated in a very specific way, something else happened, something new happened. And that these plasmas where before they squeezed them very hard, and just like squeezing a tube of toothpaste, they squirted out the ends. Now it didn't squirt out the ends. It actually pushed back. It stayed confined. It stayed trapped inside that linear topology. Even though the ends were open, the plasma didn't leave. And so there was a large amount of programs of like, what is happening here? This is an accidental discovery in plasma physics that something new is happening. And what we discovered is we now call the field reverse configuration. There's numerous programs of FRC, field reverse configuration programs, both at national labs. There's actually a number of private companies now of people building field reverse configurations. And they have some really unique properties. But fundamentally, talking about the main difference, I described a solenoid with magnetic fields throughout the center of that volume and plasma trapped going back and forth. But some other things can happen, which is really interesting. And what they discovered early is if they have field going in one direction, so the plasma, the electrical current is going around the loop and the plasma is going back and forth along this magnetic field line inside that solenoid, inside that theta patch. But then they changed the direction of the magnetic field. And this is what we call field reversal. And this is really the key, is that you start with the plasma going in one direction, and then very rapidly, you change the direction. You change the direction and reverse the direction of that field. And something really interesting happens, which is the plasma, this fusion fuel, these charged particles, which are trapped on the magnetic field lines that are moving back and forth, you change the direction. What that means is that you're trying to take that electrical current and that magnetic field and reverts its direction, flip it. But it can't flip fast enough. That the plasma is sitting there and you can't move the particles. And so what's really interesting is what happens is that because the particles can't move, but you've now flipped the direction of the magnetic field, you've inverted it, something really, really unique happens, which is that the plasma itself reconnects internally. And so now what you're left with is an outside magnetic field, an electrical coil, and inside the plasma, where now before it was moving along, it's now moving internally.
Rapidly reversing the magnetic field, plasma self-organizes into a closed field.
Mm-hmm.
What?
Yep.
So
it sounds wild.
So first of all, there's a million questions I have. So one of them, what's rapidly? What time scale are we talking about here?
Mm-hmm. You have to reverse the electrical current faster than a million degree, which is a very hot gas particle, can move. And so that means we have to do it on the order of a millionth of a second.
Wow.
We have to do it in a millionth of a second.
Wow.
And so in practice, this is hard.
Yeah.
And we can only do it now because of semiconductor switching. Mm-hmm. Because we can move things, we can switch things like the transistor in every CPU in a computer switches at a gigahertz. That means in a nanosecond. It's switching in a billionth of a second. Mm-hmm. And so now, which we didn't in the 1950s when these theta pinches were invented, but now we have the semiconductors to be able to do that.
The self-organizing plasma.
Mm-hmm.
Can you just speak to that? What the heck is it doing? How do we understand the self-organizing mechanism, the dynamics of the plasma that it's able to contain itself?
So what I like to do is use an analogy here of once you've made it, it's actually somewhat straightforward to understand. Getting to it is tricky. And how they discovered it the first time is absolutely amazing. But once you've made it, it's a lot more straightforward to understand. So, in a magnetic coil, when you have a round electrical coil, you have electrical current flowing in that coil. And if you have a conductor, if you have a metal inside that coil, and this is called Lenz's law in one of the Maxwell equations, is that as you have electrons and you have current flowing in that coil, an equal and opposite electrical current is induced in a piece of metal nearby. This is the same thing that happens in a transformer, where you have a primary on a transformer and you have electricity flowing it, and you have a secondary where electricity flows exactly the opposite direction. We use this every day in our lives. And so in this condition, you have a conductor, an electrical conductor where current can flow, and you have an electrical current flowing on the outside, electrical current flows on the inside. And in that case, now I've described two pieces of metal. Now, let's go one step further, and that inner conductor is not a piece of metal anymore. It's one of these high-temperature gases, this plasma, this charged particles. So now you have electrical current flowing in the plasma. And this is really, really interesting. We talked about these charges moving back and forth. Well, moving electrical charges is current. So in every plasma condition we've talked about, the tokamak, the theta pinch, the stellarator, there's electrical current flowing in the plasma. But in the field reverse configuration, you have a lot of electrical current flowing in the plasma, massive amounts of it. And that's the key. So you have this center core where electrical current is flowing in this transformer, if you want to think about it, primary and secondary. And here's the craziest part of it. This electrical current, how did I describe a magnet? An electromagnet is a loop that has electrical current flowing in it that generates a magnetic field. And for a theta pinch, and for a mirror, and for a tokamak, in that magnetic field, the plasma gets trapped. But in an FRC, this electrical current is the plasma. And that plasma then generates its own magnetic field. And it's then trapped on its own magnetic field.
That's fascinating.
And that's the key. And so in your tokamak, in your donut, and in your funky donut, your stellarator, you make the magnets and you trap your plasma in it. In an FRC, you make the plasma, which makes the magnets, and it traps itself. And the craziest part of this, in my mind, is that we actually see this in nature all the time. If you look at the sun, we see solar flares. And in a solar flare, we've all seen the pictures of the photosphere of the sun and this large arc of plasma coming out. That plasma has current, electrical current flowing in it. And then we see this solar flare rip off of the sun. Mm-hmm. And that solar flare then can flow throughout and continue into the solar system. And for a little while anyway, it makes something called a plasmoid. That plasmoid is, in fact, electrical current flowing in the plasma, generating a magnetic field, and holding it for longer than it would otherwise. And so we've observed these for 100 years. And we've known about these plasmoids for a long time. And there's researchers that have tried intentionally to make them. But fundamentally, that's what we do every day, is make one of these self-organized closed field plasmas.
In a more controlled way at this rapid rate of 1/1,000,000th of a second, and being able to make sure it's reliable and stable and all that kind of stuff. So, by the way, how do you keep the thing stable?
And there's the hard part, because I just described a solar flare, and yes, we've seen the pictures of them, but we've also watched them, and they appear, they fly away from the sun, and then they go away. And that's not what we want in fusion, right? We want to be able to control this. And so that's the hard part of the job. And so that's what we've spent the last number of years learning how to do ourselves and others on these pulsed closed field FRC systems. Let's first talk about how to make them, and then we'll talk about how to make them stable, because they're two different things, and we spend a lot of time on both. So we talked about timescales. You have to reverse the field. You have to change the electrical current in a millionth of a second. And so how do you do that? So I've described this system as you have a series of magnets. You have a magnetic field on the outside. And then on the inside of this, you have this donut, this FRC, that has its own electrical current. And we didn't talk about this yet, but it's generated a magnetic field. And that magnetic field has pressure. And this is the other thing that's really interesting. So we talked about how this theta pinch compresses a magnetic field. It applies a pressure on the outside. But the plasma itself has a pressure on the inside. And it has both a particle pressure, literally the particles bouncing. Think about hot gas in a balloon. The particles expanding, the ideal gas law, expanding and contracting inside a balloon. But they also have a magnetic pressure. They have the electromagnetism is pushing back. And so I like to think about this as the motor in a Tesla. In your electric car, you have a motor, electric motor. And what that motor has is a series of windings. Those windings, you flow electrical current, in this case from a battery. Hit the gas, electricity flows from the battery into the motor, into those windings, and it generates an electromagnetic force. A Lorentz force is what it's technically called. This electromagnetic force induces an electrical current on the armature, on the shaft. And this is getting into the details, but into the armature of an electrical motor that actually is what spins. And so the outside of a motor doesn't spin. You have flow electrical current through it, and the inside does spin. That electromagnetic force is what is spinning that armature. In our case, we're inducing an electrical force in that electromagnet, and that's putting electrical current, just like in the armature, into that plasma. And we can use that force to do interesting things. So that electromagnetic force can compress the fusion plasma, it can expand the fusion plasma, but here's the problem. It's unstable. And so this is something you learn very early in your graduate work as a student in fusion, is you learn about plasmas that are called high beta plasmas.
So I keep seeing this plasma beta thing everywhere. What is this ratio of plasma field energy to confining magnetic field energy? Please explain.
Plasma beta is the ratio of the magnetic pressure to the particle pressure. And so what that fundamentally means is I talked about how you have a magnetic field. And in that magnetic field, plasma is trapped on that magnetic field. But it's not very well trapped. It can escape. It can leave either down the ends, it can freely travel, or it can also travel across the magnetic field. And so we have a term called plasma beta, which gives us an understanding of how well trapped that plasma is. So as you apply a magnetic pressure, a magnetic field to this plasma, it pushes back. And does it push back a little, or does it push back a lot? And for a field reverse configuration in one of our plasmas, beta is very close to 1. In fact, usually by definition, 1 at any point in the system, which means that every time I apply a magnetic force on this donut to compress it, the plasma particles on the inside push back. And what's really interesting is you have an equation for magnetic pressure, which is B squared over 2 mu naught. The magnetic field squared is the external magnetic pressure. Any magnetic field anywhere generates this pressure. But the plasma particles themselves also have a pressure. This is the ideal gas law. And we use the definition in KT, density, Boltzmann constant, and temperature for pressure. And in high beta, they're the same. B squared over 2 mu naught is NKT. So for a known magnetic field, I know what the density and the temperature of the plasma is. And just to circle back to it, when we talked about fusion, we talked about it had to be hot enough and it had to be dense enough. And that's N and that's T. And so now I have a very clear equation between magnetic field and density and temperature of the fusion fuel. And that's really critical. All fusion plasmas have some beta, some number. The FRC has one of the highest betas, beta equal 1. However, what you also learn in school when you learn about beta the first time is you learn that high beta plasmas are typically unstable. And so the good way to think about this is a tokamak and a stellarator are stable because those plasmas that are going around in the donut, there's a force on that donut. But that plasma donut is very well held by all those magnetic fields, by all those magnetic coils. If it tried to move, it would be confined by that magnetic coil. But in an FRC is unconfined. So the plasma is confined, but the whole topology can do something what is called tilt. Is that this whole plasma donut, because it's under pressure, can just turn over. The way I think about this is think about a motor is a good example. In an armature, in the center of your motor, you have a spinning armature. You have this spinning magnet on the inside, and it is held by the main axis of the magnet. It can't go anywhere. We don't have that access. We don't have any mechanical things inside these fusion systems. They're 100 million degrees. You can't put any mechanical things inside them. And so we have nothing to hold on to it. And so it's unstable. So when you learn about the FRC, that's the first thing you learn. And it took us a number of years to learn about a parameter of how to make them stable. And that's pretty fundamental, but most people who've heard of an FRC haven't understood this really key fact. And so we have a parameter we call S star over E. And we're getting really into the physics weeds here, but
Let's go.
But it's really important. And the good analogy here is a top.
Mm-hmm.
Literally a top, spinning top. And so you have a top spinning on your desk. You know that it'll spin for a little while and then it will fall over. It is unstable. However, if you spin it fast enough, if you take a top and you spin it fast enough, put enough angular momentum, enough angular inertia into that system, it'll stay upright, even though it wants to just fall over, even though it's unstable. And we do the same thing in an FRC. is if you can drive it fast enough, if you can add enough kinetic energy and inertia to the particles, it will stay stable. However, you can do another really key thing. We are not limited now to having a very skinny top. We can actually make it much bigger. So the good analogy here is if you have a coin and you know you're spinning that coin, if you spin it faster and faster, it'll stay spinning longer. However, eventually it'll slow down and fall over. But if you had a roll of duct tape, if you had something thicker and heavier and longer, and it's spinning around that same axis, it'll stay spinning even longer, both because of the inertia and because of the geometry. And so we have this parameter called S star over E. S star is the hybrid kinetic parameter, which tells you how stable it is from that top point of view, and the E, which is the elongation of how long it is. And so maybe fortuitously, thank you, nature, gave us a win here, which is that how we make these in these long solenoids is naturally very, very long. And so we can build these with very long lengths. And if we can drive them fast enough and hard enough and drive the ions to move at very high velocities, we can stabilize against those instabilities and hold them stable. And so we now know we can design with a given S star over E parameter, we can design these for very long lives. The theory of the systems we make say that they should last for a few microseconds at most. Us and others in the field have been able to make them last for thousands of microseconds, thousands of times what the stability, the basic criteria would tell you. And so we know now how to do this. And so we just design them with this built into them.
Can you explain a little bit more of that star over E? Are you given that, or is that an emergent thing? So, like, at which stage is that the result or the requirement?
It's a great question. So it is a requirement of the system, is that you must design it with this parameter in mind.
Got it.
The hard part is you have to design it with S star over E being satisfied the whole time.
Right.
And here's the extra trick here. S star over E is also a measure of temperature.
Oh, boy.
And yep, it all comes back to temperature. The hotter you make them is the same thing. Temperature is kinetic energy. Is the faster you're spinning. So if you take your top and you spin it faster, it's more stable. But you've got to make it hot. And so here's the trick. How do you make something hot that's starting cold? And it has to be hot by definition. And so that's part of the challenge of what we do day to day is getting to these hot plasmas. And where other people have tried to make FRCs and not been very successful, it's because they couldn't get it hot enough fast enough. Is it fell over, it tilted before it got hot. And so we spend a lot of our electrical engineering. In some ways, Helion is more of an electrical engineering company than a fusion company some days, focusing on how to make the electronics fast enough to be able to get it hot enough soon enough that you can keep it stable the whole time.
So you're trying to reach 100 million degrees. How do you get to that temperature fast? And by the way, what can you say to help somebody like me understand what 100 million degrees is like? It seems insane. What does that world look like? I guess just everything is moving really fast. Like you said, you can't put anything mechanical in there.
Yeah, so a couple of key things happen. So when gas is that hot, we talk about the states of matter. You have solids where ice, it's cold. The atoms are now bound in a lattice structure together. They're held together. And then liquid, you've broken a lot of that lattice structure. They can move around. They have some kinetic energy, but they're still pretty contained. They stay in the bowl. Keep heating it. Now you're in gas. And now these particles are free to move around. They're moving around. They're bouncing off of each other all the time. And you can keep heating it from there. And that's where we talk about some more phases of matter. We can add a little bit more physics here. We talk about rarefied gases. So when we think about most gases that humans interact with, they act like a fluid. And what I mean by that is that they're colliding with each other so often that the particles at any one place here, the air is roughly the same temperature as the air here. That these particles are bouncing off of each other. If you put a really hot one right here, it would then cool enough that all the air is roughly on the same temperature. But you can be what is called rarefied. And this is like space. This is where now you have particles moving around, but they don't collide with each other very often. And so you can have one very, very high energy particle and very cold energy particle, and they may not even touch each other, but maybe occasionally they bang into each other, they collide, and then they transfer energy. And that's where we call rarefied. And then you can go even hotter than that. And that's where now the actual atomic states, which has the nucleus, which is a proton and a neutron, and an electron, gets so hot that electron gets energized and then escapes, leaves the system. And now they're charged. You have a positive nucleus and a negative electron floating out. And that happens on the order of 10,000 degrees. So way hotter than what we're used to. But now we're going to go hotter. We're going to take this plasma and go even hotter. And what does that mean? At that point, a lot of the way we think about temperature doesn't really apply. The idea that you have these random motion of particles, because now they're all individual particles moving at very high velocities. So what it's really is a measurement of is velocity. It's really a measurement of how fast is that particle moving. And that's how I really think about temperature when you get to that 100 million degrees. And so it does some more complex things. If you have this high energy particle, that's why we like fusion, is moving at high velocity, and there's another one moving at high velocity, they will come together, they will collide, and they will fuse. Mm-hmm. But other things will happen. You don't want to touch that high velocity particle with any kind of material, because it will collide with that material, damage that material, and usually like blow off some chunks of that material. Mm-hmm. So we don't do that. We keep those charged particles in a magnetic field. So they just bounce around and they don't ever touch anything. And that's really important. And so it's less thinking about it from the way we normally think about hot and cold, and more thinking about it from a velocity point of view.
So what we should be imagining is extremely fast moving. What is it? 1 million miles per hour? Is that accurate?
That's the right kind of order for these systems.
Crazy. And so you're looking for them to collide. Well, first of all, to get back, is there some interesting insights, tricks, anything you could say to the complexity of the problem of getting it to that high temperature quickly?
So if temperature is velocity, that means they're moving quickly over a given amount of space. Speed is distance divided by time. And so if you have a machine of a certain size and it's moving very fast, that tells you the time that particle is moving from place to place in that machine. And in fact, if it's 1 million miles per hour, these are on the order of 100 kilometers per second, which you can flip that around and you can say you're moving at meters per microsecond. Mm-hmm. So feet per millionth of a second. And so that fundamentally tells you, and we've known this, as soon as you say, I want to do fusion, you know you need to react to the universe in microseconds and be able to understand the system in that speed. And if you get it hotter, it goes even faster, and you have to go faster. And so we look at those, and that's how we think about the systems. We measure everything in microseconds, not in seconds. And so when you do fusion, it's pretty wild. It's literally a flash. Fusion happens. Mm-hmm. And it's over. You start it, you do a lot of fusion, you recover energy from it, and then you turn it off before the human eye can really respond even.
And there's a computer managing all this. Like, how do you even program these kinds of systems to do the switching? Is there some innovation required there?
So I'm continuously amazed by what the pioneers in fusion were able to do before the computer existed, because they had to control things at this scale. But maybe it was pretty hard, and why we've been able to take what they did and build on it, because now we use modern gigahertz scale computing to be able to do this. And so even when I started my career, we talked about like megahertz processors. Megahertz is microseconds. That's great. You're kind of at the border of fast enough, but you can't do computation at that speed if all it can do is respond in 1 microsecond. But now gigahertz means I can do 1,000 operations in that 1 microsecond, so I can do more useful things. So we use mostly, this is way too fast for any human to respond to. So we use what's called programmable logic. So we program in sequences to the fusion system to be able to do this reversal. We pre-program it, and then we run a sequence, and then fusion happens. And so in this sequence, programming language, we use a variety of them. Some of the fusion codes are actually written in Fortran still.
Nice.
And though a lot is now more and more run in Python. And so we do a lot of Python, we do some Java, and then we also have because of the speed of this, it's a lot of assembly language programming.
Mhm.
So we go right to the assembly level of the programmable logic, FPGAs, and we program those. And so to be able to run one of these systems, we typically have a series of electrical switches that turn on this electrical current. Those are controlled via fiber optic because the wires are just too slow. And so fiber optic, I can send photons at the speed of light. And so those fiber optics can respond in nanoseconds. And then I trigger those fiber optics with programmable logic that we've programmed in the hardware assembly language.